Good afternoon again. We now have 6 people at 2:10, so we're going to get started. Could somebody just remind the whole group what we're looking at? What's our area that we are looking at specifically right now? I'm listening. Hello? What area of mathematics you're?
We were looking at algebra.
Yeah, we're looking at algebra. And why are we looking at algebra?
Because all other topics are intertwined with algebra.
That's correct.
And it seems to be a very problematic area in mathematics.
Yes, for people who have to transition from dealing mainly with whole numbers to get their heads into and transition successfully with dealing with variables and unknowns. We refer to algebra as the gatekeeper to higher mathematics. Isn't that so?
We do.
Yes, we refer to algebra as the gatekeeper because what we are doing in algebra mainly is we are transitioning to a place where we can generalize. And so people find it difficult because they understand whole numbers, and that has been really pounded into their heads for a number of years. And although there are many people who believe that algebra can be intertwined in the primary school curriculum, some people shy away from it. And that is a result of many different reasons. The thing is that some of the primary school teachers are not comfortable dealing with variables. Some of it has to do with how the curriculum is written. And some of it has to do with the new thrust in math that is not completely adopted by the way the curriculum is written. Because we discussed the other day that for a problem-solving approach to be considered through the whole mathematics curriculum, it would have to be rewritten to reflect that. What we have now mainly closed-ended problems where we have an answer and we say yes, and we move on from there to the next topic, and have some more problems where we get an answer for it. And as we look at problem solving, and mathematics by nature lends itself to that, but somehow we are not fully focused on that, and our curriculum as it is currently written reflects that. Now, let me write something on the board for you. Hopefully you can see it. And I'm going to ask you a question. I have 5x plus 2 equal to, let me see, say minus 2. I'm making this up. 5x minus 2 is equal to 13. And if I have an expression 2n, right? I want n in both. I want n in both. I have 5x minus 2 is equal to 13, and I have 2n. I want you to give the same variable 2 different names. You know, we look for in the first one, we're looking for what?
N.
We're looking for n, yes? And can we find the value of n? Can we find the value of n? You don't have to do the problem, we're just talking about it.
Yes, we can.
Yes, we can find the value of n. All right, now, suppose we don't know how to solve an equation, right? We don't know how to solve the first equation. What could we do if we don't know how to transpose and all of that kind of stuff? How could we, what's an alternative way of trying to solve that equation? We could do what?
Trial and error.
Yes, we could do trial and error, but you can be more specific.
Substituting.
Substitute different numbers for x. But what do we understand by an equation?
Both sides are equal.
Are equivalent. How do we know when we got, if we're using trial and error method, right? If we're using trial and error method, when would we know that we have reached the correct solution?
When the value we substituted on for the n balances the left-hand side with the right-hand side of the equation.
Okay. So will any number do? Will any number substituted do?
No.
Okay. All right. Now, look at 2n. Suppose I do the same thing. Will any number substituted work for this?
Yes, any number would, because that's an expression.
This is an expression, right? And this one is a
equation.
So we could describe n in here different from the n here. In this case, we're finding the unknown value, right? So in here, we could call n the unknown, but down here, it's strictly the V word that we have been studying. Do we see that? Is this making sense to anybody? Here, n would be the unknown, yes? Right here, n would be the unknown value. Because once you get the value that balances both sides, you're done. It will not change. It cannot be what it wants to be. It is limited by the fact that it is a unknown value. And once you know the value, that's it. But in this expression, right, I could have this n described as a variable, because nothing is going, any value you substitute here, you will get a different value for 2n. So an unknown value and a variable have slightly different meaning and different implications. Do we see that? We have different implications. So now, sometimes there are equations that we could write, and sometimes people refer to them as identities, where any value will do. Any value that you substitute for n, in that case, it would, or x or whatever the variable might be, it would be considered a variable. So here, n is considered as an unknown, and here, n is considered as a variable. Now, if I have a minus b plus b is equal to a, any substitutions I make for that will be okay. Do you see that? So here, probably could say that these are variables. They would give different values, but they would be equal all of the time. Here, so here in this case, n would be the variable, and here we would have, because the opposites here, the additive inverses would cancel, and I'm just left with a is equal to a, which is the what? What kind of properties a equals a? It has no property name. What's the property name? So it's reflexive.
Reflexive.
Yeah.
That's right.
Eh?
Reflexive.
Yeah. Because it points back to you.
Right.
Yeah. Mm. Okay. So the thing is that we have looked at some of these, and so every time you see a variable, you see a letter, sometimes it should be described as an unknown, especially it can only be represented, correctly be represented by one number value. All right. We looked at the teaching and learning of algebra because, as Jeffrey says, that, you know, that's one of the critical bridges that must be crossed successfully in order to experience success further up the line. We look at the early ideas fostered in the primary years. We looked at that, and we saw that students have a bridge. There's a bridge that we must cross because we must be learning to generalize, yes? And we looked at the core algebraic ideas, and that centers around unknowns and variables, right? We have to go through collecting like terms. We should know what like terms are. I'm going over some of what we did the last time. So in core algebraic ideas, we have to look at a difference between the unknown and the variable. If the letter or the alphabet appears in an equation, we generally refer to it as the unknown. If we have an equation where we have several terms with the same variable and the same exponent, we call them like terms, and we may gather them in order to find out what is the value in that particular context. Because we know that variables in an equation, a variable in an equation must have the same number. So if I have a term with a variable on both sides of the equation, I cannot have an n over here with one value and on the right side have the same variable n with another value. It must be the same value, right? So we have generational and we have our transitional activities. We have to learn those if we are going to be successful, because we have to move things, gather things. We have to look at the context in which the variable is presented and know whether it is an unknown or it is a variable. We have to look at equivalence and variable. We know about equivalence and we talk about that. Now, equivalence, a conception of symmetric and transitive quality, of transitive character of equality. Now, the last time we were talking about that, the time before the last, we spoke about transitive, and we did not say it expressly. Can anybody tell me what is the transitive property? Transitive property. Anybody remember what that is? Have you heard the word before? Have you heard the expression before? Hello?
Yes, we have. I'm trying to recall what I.
Transitive means that if one quantity is equal to another, okay, if A equals B and B equals C, then A is equal to C.
Yes, so that's a nice way to put it, because the thing is that you have given yourself an angle to use. You don't say if one quantity is equal to another quantity. We could say given A, B, and C, given A, B, and C, and you said it perfectly. Would you say it again, please? We're given A, B,
Given A, B, and C, if A is equal to B and B is equal to C, then A must be equal to C.
yes. So we are given, I want to erase this so I can write in the same spot so you can see what is happening. Given A, B, and C, right? If A equals B and B equals C, then A equals C, right? Where is the bridge? What forms the bridge? Where does A climb to the over what to be related to C? What's the bridge here?
B is the bridge.
Bridge, right? Because A equals B, B equals C. If this is the case, then we know that A is equal to C. And so we have that. And a student coming from primary school to high school has to have a bridge. And what is the bridge that we look at? And we have to keep looking at it all through high school. What did they bring with them? They are mostly related to what? What kind of numbers in primary school?
Fractions?
Pardon me? What?
Guessing, is it fractions?
No, that is not what we discussed. They were exposed to fractions, but the numbers, the set that they're most closely steeped in is the set of whole numbers. Whole numbers, because they call it fractions, which is another set of numbers, but they do not introduce them to the rationals and irrationals and reals as yet, although we know that. So here, our students, remember we said that if we were able to line up parallel situations between algebra and something that they are so familiar with, the whole numbers, then probably they would make the transition a little bit better. They would not be turned off, because the fact is they are coming from primary school with some knowledge of numbers, mainly whole numbers. So here we have a situation where the transitive property is given in this form, and you have to remember it because it comes up. And remember, I said the beautiful thing about mathematics is that what you learn in kindergarten, you learn it when you become a rocket scientist. It doesn't change, it gets more sophisticated, because the same reflexive property, same associative property, and all those, we use them again to define other entities. Now, who can give a real life experience to explain this to a student? They might be in the 8th grade, I don't know. Who can think of a real life experience to explain this relationship? A, you can say A is related to B, B is related to C, therefore A is related to C. Who can give a real life experience for this?
You mentioned related, so we could actually use family members.
Yeah, you could. Yes, I was trying to give it away so people would think. So, because you don't have to have equal here all the time. What other kind of signs we can have here instead of equals? Other notational items in mathematics.
Inequality sign?
Yes, you can have inequality sign. If A is greater than B, right? And B is greater than C, then A is greater than C. And could we use a numerical example to show that?
We can.
That should be very easy. So if I am showing this to somebody and my student is there puzzled, not voicing it, but saying, transitive, what kind of a thing structure is this? What is it? Why? You know? And you can put up something that is related, right? If A is greater than, you can say older than B, and B is older than C, then A must be older than C. So we can put it in all different kinds of contexts in order for our students to get a hold of what we are trying to say. Because this is one of the foundational things in mathematics. We call them axioms because we just use them. We just use them. We don't have to go and prove them. But if we put them in terms of numbers, we really don't need any proof. Okay? So we look at relational symbols and say that the two terms are equivalent, or the two expressions are equivalent, right? Now, we looked at that. So what do we look at again when we're starting? We looked at early algebraic ideas fostered in the primary years. They know about signs, they know about finding missing things. We would say finding the unknown. But they have to cross a bridge because we are trying to get them to generalize. But they know the equality principle. They know it is the same as, because some teachers teach the equal sign to say it's the same as. Then we look at the core ideas, where they have to look at the unknowns and look at variables. Then we look at equivalence relationship. And there is something in discrete mathematics, which is a precursor to abstract algebra, which satisfying three different laws of mathematics. We say it's an equivalence relationship, and that will come later. They might not even be exposed to that, because the people who at one point high schools were teaching discrete math, and now the high school where I came from, we're trying to push them straight into calculus and drop the discrete mathematics. Then we developed the idea of variability to reach the point where we can generalize, right? Variable provides the algebraic tool for expressing generalizations in mathematics. Yes? Variables provide the algebraic tool for expressing generalizations in mathematics. Remember, we say it is fundamentally different from what we call the unknown. An unknown number does not vary. Is that true? An unknown number does not vary.
True.
And a variable can change and still be a valid response. Variables are numbers that can change and provide a valid response. Okay? When we look at the literal symbol, the context in which the symbol appears will tell us whether it's an unknown or it is a variable. All right? Now, we looked at that already, and we looked at 2n plus 3 the last time, and we looked at 3n, and we looked at n plus 6. And we asked if they can be an unknown or it is a variable in the different instances. And we went through that. Okay? Now, we also looked at the transition to algebraic thinking. You should be able to fill in anything that you missed the last time because you should have these topics. The transition to algebraic thinking. And we said nothing is wrong with their brains, but the way it is presented is determining factor whether they are able to make that transition or not. And we said that if we were able to provide parallel examples in arithmetic, then we would seem to be able to give them some place where they're anchored and move them along a little bit more when we are introducing the variables. Now, we also said transition to algebraic thinking is accompanied by some new, what? Some new notations, yes? And some new definitions, some new words. The thing is that as teachers, this is just a comment now, as teachers, we have to realize that the transition might be a sticky point. And so we have to make that road as smooth as possible. Sometimes we are going into a territory with which we are not quite familiar. But if we are able to hold the hand of somebody we think who is more experienced and has been to that place before, we feel a lot more comfortable. So the same idea translates to when we are saying, you might not have seen this before, but you have seen A plus B equal, you have seen A plus B equal B plus A in another form. 3 plus 5 is equal to 5 plus 3. So one is the arithmetic and one is the variable. So we know if we add A to B and then add B to A, we have the same amount. And we can illustrate that by using whole numbers with which they are quite familiar. Do we understand that? So what we're doing, we're using arithmetic to escort them into algebraic thinking. Yes? Because they're transitioning. And it's no fault of their own. They're coming armed with what they have been taught. And so therefore, we know that you're very comfortable. As I said once before, if a person is being tested or being questioned in a language that is not their primary language, they will not do as good a job as if they were questioned or interviewed in their own language. And I have seen that before from personal experience. I think last semester I told you that I had a student who was tested she's Spanish speaking, and she was tested in English. And that was a diagnostic test. And the way the test came out, she was placed in a lower mathematics course than she needed to be. So I didn't know what transpired while the child was there. I welcome students, I don't test them and I don't place them. But this little girl, she was doing so well in the math that I suspected that I was way below what she could be challenged by in terms of the types of problems that was dictated by the level at which she was placed. And it was so troubling to me that I went to the counselor. I went to the counselor and I said, this child is just making A's with her eyes closed. What is the problem? And I found out that she was tested by those people who do diagnostic work. And so I got onto that person and I said, would it be possible to find a person who could test her in Spanish? Lo and behold, she was like 3 grade levels above what they were saying. She came from a war-torn country to America, and she was in a new environment. She was in new everything, and they decided that her age factor was not what placed her, but her proficiency in mathematics. And I found out that she knew more mathematics than way above the level, and she was 3 grade levels above, so she could actually have been placed where her age, yes, because Costa Rica and those Central American countries have conflict lasting many, many years. So when they saw the level at which she tested out, being tested in English, they count it to war. They just say, you know, she must have had interruptions in her academic work and her academic schooling, I should say, and she was placed. And when I saw this girl was just ripping through the math, she was just ripping through. And I said, no. This is more than meets the eye. We should go back and investigate. Now, the thing is that the fact that I was able to make that determination got the student placed at the proper level. And you know that sometimes you have students who, she couldn't argue with me because she didn't have the skills to argue with me. But I was able to see what I expect to take a certain amount of time. She was done and over with it. She could do it in her head. And so I got a hold of it, and then I got a hold of the counselor, and then we got a hold of where she was tested. And we got her tested in Spanish instead of English. And she shone. So that was a good ending to that story. Now, a generalization and word problem solving approach to transition. I think we were there. That's where we should begin this time. So that's your other subheading. Transition to algebraic thinking, we said. They need to learn generalization. We can escort them using arithmetic. And they have to learn some symbols and notations. Now, this person, this researcher, used, his name is Bernards, and I think I gave you that already, used a problem-solving context involving word problem to stimulate the emergence and development of algebraic procedure in 7th and 8th graders. He had 3 teaching sequences. They were developed, the first one was developed where the letters used had different meanings. If the letters are used have different meanings, right, it can form a pattern. And we know that being more experienced than the student, we know that sometimes we have a formula which will work for any one of the terms in the sequence. Yes, we know that. So the letters were used that had different meanings, such as a generalized number in a number pattern formula, and an unknown quantity in a word problem solving. So the thing is, he used it in the 2 contexts that I explained on the board. The first one was designed to ensure that students understand the importance of transition to algebra in the context of generalization, because that's what it's all about. Algebra's, one of the definitions is that it's a generalization of arithmetic. So it has sort of the same characteristics and structures. It's just that we have to learn some things like transposing and collecting and so on, which we do not generally do in the times when we're using whole numbers. And generally whole numbers give you one answer, but probably the answer after we have done collecting and transposing, we might get 2a plus 2b as our answer, and we are not able to give one number as they're accustomed to in arithmetic. Okay? Now, we have number patterns. We remember that we had a pattern on the board the other day, and we see that +1 was the common part, and we have 4 arms in the shape of a cross, and the arms are the variables. So in that context, the letter that is used would be a variable, because you need a different number of blocks in each succeeding array, in each succeeding pattern. He also introduced, which I've said it 100 times if I've said it once, the second teaching sequence, the student focused on arithmetic comparisons in word problems. The third sequence dealt with the solution of algebraic problems, focusing on mathematical generalizations and comparisons. So he upped the ante as he went along. He upped the ante as he went along. In this sequence, there was a starting situation for students to reflect on the choice of the generator, which is the variable. The writing, second phase, they have to reflect on it, then they have to write verbally. What is this saying to me? What is this saying to me? You have to write. And you know that there is writing in mathematics. There's reading in mathematics. And this person has to interpret what it is they're seeing or given in writing. So they have to write a verbal statement to account for how a quantity might be calculated. That means, what are they going to employ? What's their approach? And the changing of one of the quantities in the situation to reflect the impact, so students could see the applicability of the verbal description. to the whole class of problems. And if you're given one problem and you can use the letter that's used in the problem as a variable, it could apply to the whole class of problems. I'm going to try to give you an example. What do we know about volume? We know something about volume. Volume is what? Volume, say, of
the area of
yes.
the area of the base times the height.
Times the height, right? Now, are those variables or those unknowns? We have how many unknowns there? We have how many letters we're using?
A times H.
Yes, but we have to use something to get the area. So let us write it out.
Yes.
We have to determine the volume of a rectangular, you call it something that I don't call it, but a rectangular prism, I'm going to say. Do we understand rectangular prism?
Yes.
All right, rectangular prism. Rectangular prism is, how do we know a prism different from a what? A prism has the same top and bottom. You can turn it over and it can sit. But if we have a pyramid, then we might have a rectangular base and anything up the top, right? So a pyramid and a prism are two different things. But I think you call it something else, something with an oid at the end.
Cuboid.
Cuboid, right, yes, okay. So the thing is, if I have a rectangular prism, the volume is equal to
Length times base times height.
Base area times
Height.
Now, are the L, the W, and the H, are those unknowns or are they variables? Hello?
Unknowns.
If
Because if it's equal to a certain volume, then it will be an on.
all right.
But if you're looking at the general formula, you would refer to mass variable.
So if I say my volume is 64 cubic units, whatever the units turn out to be, then, and don't tell you anything else, then my L, W, and H are variables because I can play. Do you see what I'm saying? I can assign different values, right, to get to the number. But if I'm supposed to find the volume and I have three letters, L, W, and H, I have to be given 2 to find the third because I only have one equation. So if I'm not given a numerical value for the volume, what I could do, and if I'm given replacements for L and W, then my H now could be a variable and I could get different volumes by varying, by changing the values of H. Do we see that? All right, so the person must be able to give a verbal description of what is happening in that problem. Now, we use a problem solving approach with verbal descriptions, as we said, that the students are generated. The relations in these problems were then made more complex And finally, there was extension. So you can have different levels to the problem, just like how we talked it out. If we have a volume, then we can vary. That is more sophisticated. If we are given the length, the width, and the height, then those are the unknowns were replaced with known values. So you get the volume as an unknown. But if we were to say, okay, what to generalize, we could get two of the values to determine, what we can vary the volume for in as many directions as we wish. Listen to this very carefully. Something to do with a warehouse generalization problem. I'm going to say it slowly so that you can get what it is we're talking about. The starting situation is this. A son hired by his father to do an inventory left him, that means the son left this, the following message. The son left his father the following message. 3 types of articles were counted. 3 types of articles were counted. Here we go. There are 2 times more rackets than balls. It was a hockey warehouse. And 3 times more hockey sticks than rackets. You want me to repeat it? Would you like me to repeat it?
Last statement, yes.
Yes.
3 types of articles were counted. There were rackets, balls, and hockey sticks, right? The son said there are 2 times more rackets than balls, and 3 times more hockey sticks than rackets. Do we have an expression for all of those? How many things we have to deal with? How many things we have to deal with?
3 things.
3 things. So the first thing that we're going to do is to represent it in writing. We're going to represent the situation in writing. So we have what? Hockey sticks. We have hockey sticks. We have, and we have what else? We have
Rackets. Rackets. Rackets.
All right. So we want to find expressions for this because this is our writing phase. So what did he say the first thing? There are 2 times more rackets than balls. So what you going to say? What you going to say there? What's the first thing we are going to name? All right, so what are we going to call it? We can call it N. X. Okay, X. All right. So then, how we are going to represent rackets?
2x.
All right, so we have 2x. How are we going to represent hockey sticks. 3 times more hockey sticks than rackets. So we're going to say what?
6x.
So let us do this. 3 times more, right? Just to be very explicit. Do we see that?
Yes,
Now, who wants to ask a question? What do you think is that question? Do you think the father understood what was in the warehouse? Class, I'm talking to you. Do you think the father knows what was in the warehouse? What does he really know? Yes, but what he doesn't know?
The quantities.
The quantity, right? The quantity. So in this case, X could be, X is what kind of number here? What is it, variable or unknown?
Variable right now.
Variable right now. Do we see that? Am I making sense to the rest of the people who are not participating?
Yes, you are.
Okay. So when the father comes in, right? The father comes in and he sees all these X's, or the statement that it was expressed in writing. Now we're going a little bit. This is called, one is writing, one is representation. So this is like a graph or something semi-abstract, right? Yes? Because here we are going to work with this. And the father really doesn't know what is in the warehouse. What is a remedy for this? To find out how many of each are there. What is the remedy?
If he finds out how many balls, then he can find out how many rackets and how many hockey sticks.
How can we?
By counting or checking.
But we are not there, darling. So what is missing from the son's message that he left his father?
The total number of items in the warehouse.
Total number of items. Because that many hockey sticks, that many balls, that many rackets cannot be determined unless we have the total number of items that were in the warehouse. So I think the son was playing a little game with the father, because the father cannot tell what he is to do, because this information could lead to decision making on the father's part as to what he would order to bring to the warehouse based on past experience at the movement of these different items by customers. Do we see that? So this, what the son tells the father, is not as helpful as if he was able to say total number of items. So you hit the nail on the head. So let me see there. So if I said to you there were 270 items in the warehouse, could we now find out? All right. So
Yes, we can.
pardon me?
Yes, we can.
Yes, we could find out the number of each of the items that were in the warehouse. Now, if we can get our kids to understand this, right? That right now we have a name for these things, but the name is not explicit enough. The name is not explicit enough. So we would have to have something else in order for us to determine what it is that we have in the warehouse in terms of each of them. So we would have to, so what is involved here for the student now to determine this? What skill would they have to know? They have to know some notation. They have to decide what they're going to bring to the table. What are we bringing to the table here? in order to determine the exact value of each of the items?
Forming equations.
Forming equations. All right, somebody else beside Jeff or Ann. Let me call somebody. Who's that I'm going to call? Miss James, what are we going to do there?
What are we going to do where?
To find out the number of each item that is in the warehouse. We said there are 270 items.
Mm-hmm. Yeah, that.
Determine how many.
So we can form an equation based on the number.
Yes, so students have to be helped to find out what to do. So what would you do? What would you tell them?
Well, if the warehouse has the 3 items that we have on the board, then we have to understand that the total number of all these items will be the 200 and, you said, right? Items that are in the warehouse.
Yes. And so we have to talk to our students. We have to talk to them, right?
Right. So then if all these items are there, then we will say that the sum of all these items, because remember each item is represented by an algebraic expression, so we can also say that the sum of all the expressions, the value of the sum, will be equal to the total number of items in the warehouse. So we can make equation, a mathematical sentence to be the equation showing that information.
Yes, the mathematical sentence, you were right. So the thing about this is that the 270 represent all together, and probably we could use equal, we could use all together, you know, and you're going to stress the word in order to give them the cues. So now we don't need to solve that problem. The only reason why I would solve it is that when we get the value of x, are we done? Are we done?
No, we need to find the
Yeah.
number of
We
pieces
have
around.
to go back. When we find the value of x, we have found the number of blank that is in the warehouse. What is that one? When we find the value of x, what are we?
Number of balls.
Number of balls. And then what you have to encourage our students to do is to remember what is required. What is required. So if we want to find out how many rackets, how many hockey sticks, and how many balls are in the warehouse, then we have to help them to recognize that since balls has the name X, they could go back to this situation and put another equal sign right there. Do we see that? And then we have a numerical value for every different group of items that are, for all 3 groups of items that are currently in the warehouse. So if I'm left with, suppose somebody says, notice that I sold more hockey sticks than any of the 3 items in the warehouse, and balls is the slowest moving item that I have there, and rackets are the next higher. So if I'm going to put a hierarchy to the balls, rackets, and hockey sticks. Do we see that? Now, if entrepreneur, if a owner, if a business person sees that they have this because of the movement of the items, right? Then they could say, I want 6 times as many balls as hockey sticks. No, 6 times as many hockey sticks as balls, and I want twice as many rackets as balls. because of the experience and the flow of the items out of the business entity, then this part is good enough. But if I say my inventory is that, then I can find out each of how many I have there. And that's a transition. Do we see that? All right. So the person is encouraged to find the amount, or they can argue about what is reflected in each of the expressions. Yes? Hello?
Yes.
All right. Now, if I say that there are 3 more rackets than balls, right? And 4 times more hockey sticks than rackets, then I have a different problem. Yes? And I also would have to say how many articles there are in the warehouse. How many, if I give you a number, then I can ask that question. How many of each are there in the warehouse? All right? Now, students can use various modes of representation. What modes have we used in this problem? What have we used while we were talking about this? We spoke.
I did. I said visual aid, drawing, diagrams.
That's correct, yes. Diagrams are semi-abstract, right?
Okay.
And so we can have, probably we could have, for even a little child can do this in primary school if we give them the different things to be represented, manipulatives to represent the different things, right? They could show that. And if we do some of that in primary school, it will be planting the seeds for high school. The thing is that we have written language. We can write it down. That's the first thing we did. You wrote it down, I did not. I gave it to you verbally. So you wrote it down, right? Yes? Then you can represent the quantities. You can draw the things. You can even draw rackets, or you can draw hockey sticks, or you can do whatever. That is the semi-abstract. Do you see that we are climbing? We wrote it down. We interpreted it by using icons. Iconic representation of the quantities. Then we looked at how to express it symbolically. Yes? Symbolically, we call the balls X, and everything has to be named with X in it. Because if we ever introduce another variable, we cannot solve the equation. So this is like the fundamental approach to transition to algebraic reasoning. We are constructing meaning. We are constructing meaning as we go along. We have to use notation. They came up through primary school using equal sign and using equal sign and using, but we had to form an equation with equivalent entities, one on either side. One was a whole number, and the other one were expressed in 3 terms. So there we get the equivalence. Then we had the discussion. So what are we doing here? We are building the situation. We are building. So here, the fundamental components to the transition is to write, represent, discuss, those kinds of things in order to get to the solution. And I said earlier that we have to use notation and what notation means. It is very, very important that we have a discussion in order that the students can see how the reasoning process evolves and construct meaning from that. All right, what I want you to do now is to draw a semicircle with diameter of 60 units. Draw a semicircle with diameter of 60 units.
Six zero.
You can draw any length to represent 60 units, you know. So we're going to draw a semicircle. Divide the diameter into 3 equal lengths. All right, so this is my 60 units, whatever you want to call it, right? Now divide diameter into 3 equal segments. Are we getting it, everybody? Hello? Are we getting it?
Yeah.
Yes, yeah.
Yes, all right. Now I want you to draw semicircles on each of these segments. Draw semicircles on each of those segments. How many times would a child see semicircle in everyday language? How many times would a child see the word semicircle in everyday language? You know, informal conversations and all of that and all of that.
Not very often.
Not very often. So it is our job to ensure that our students know what's a semicircle. What else they have to know?
Diameter.
Yes, we're talking to the class, yes.
What a diameter is.
Yeah, we have to find out what constitutes a diameter, right? And so we have to talk about that. Now, if you are just going into this problem without making sure that the student knows what these are, they might be confused. Okay? So what we do, we say, Now, it's not important that it's exactly right. If a child picks up a ruler and wants to make sure and take 5 minutes to know what is the 3 equal parts, that is not very necessary. But we're just going to assume that where we put these little blocks, it is the equal parts, okay? Now, what I want you to do is to draw a semicircle on each of these segments, touching. So, do you have that picture?
We do.
Your participation by inspection or by doing?
Doing.
Okay, are we there? Are we there? Class?
Yes, we are.
Okay, all right. Okay, now, write a number sentence to compare the length of the arc of, which one? Oh, let me put some numbers. Let me put some A, B, C, right? What is A, B, C considered to be? I just call the name. Is it an arc? Is it an arc? Class, is it an arc?
Yes.
Yes, it is.
Oh, yes.
So you have to write a number sentence to compare the length of the arc of the large semicircle to the total length of the arcs of the 3 smaller semicircles. So right in there, the student has to bring something to the table. What is it they have to bring to the table?
Finding the length of an arc.
Yes, but it can be more specific than that.
That the length of the arc of the semicircle is half the circumference of the entire circle. So
Right, so my students would have to know about that big word,
circumference.
circumference, yes. My students would have to know how I find the circumference of a circle and what to do to find the length of this arc right here. Okay? So what are we going to write? What's the length of this arc? A, B, C. Somebody? Hello? What is the formula for finding the circumference of a circle?
2 pi r.
2 pi r, yes? Or another way, that David is saying,
Pi by
pi times the diameter. So now you are going to write the length of the arc for the first semicircle and write the length of the arc for the sum of the 3 semicircles. What you're going to get. Somebody say what is the length of the arc on the big semicircle?
Thirty units times pi.
30 pi. Everybody agrees?
yes.
Yes.
Yes, I do.
30 pi, yes? 30 pi. Now, What I want you to do is to use the original semicircle, but instead of dividing the diameter in 3 equal parts, I'd like to divide it into 4 equal parts and see what you get. But you have to first tell me what is the length of the arc for these 3 and how is it related to the big one.
Each of them will be 10 pi. You hearing me?
No. What's this diameter right here?
20.
Yes.
So half of 20 is 10. So each of them is 10 pi. So together they make the same 30 pi.
So if you were to divide the diameter into 4 equal parts, what would you get? Because the result here is that when you do this, you get the same thing, right? Now, well, 30, 10, 10, 10, right? So if you divided the diameter into 4 equal parts, you're going to get what?
The same 30. 30 pi, sorry.
So can we guess now, or do we have to do another one? Suppose we have 10 small semicircles. So what are we doing? What are we doing? What is a big word for this? We are saying, what is a statement we can make based on our experience? And we talk about this. What is the whole idea of algebra? Generalize. So could we generalize something about this? Could we make a general statement about this? Anybody would like to make a general statement about this? What we have experienced here? Should I go to sleep and take a nap?
Okay, let me try. That the length of the arc of the semicircle is equal to the sum. Okay, the sum of the semicircles that can be made from the diameter, from its diameter.
No matter
how many semicircles that are made, no matter the number of semicircles that are made from the major diameter.
Exactly. So you see, we're generalizing. So the n in the top half of the circle, right, are variables, right? But this guy, for the first circle, it is a constant because it's 60. Do we see that? But we're saying no matter how many subdivisions we make and form semicircles, the sum of the arcs on the semicircle will be the same as the arc on the larger circle, semicircle. Do we see that? That is an example of being able to generalize. You're being able to generalize from experience, right? You know that there is a general equation for the sum of the first 2 whole numbers, sum of the first 2 natural numbers, the sum of the first 3, and so on as you go on. There's general, where you can say if you want the third one, you know what you're going to get, right? So that is a situation where we have the opportunity to make a generalization. And there is where you will get writing. You are not here to show me your writing, but you verbalize it, and that is sufficient. So if you look at the number sentences that you have written from the different divisions, you see the same result. And so you can go from specific to general. Yes? So that is one thing that students have to be talking about. They have to be able to generalize. They have to be able to generalize. Okay? When you look at part A, right, the students will look across a series of number sentences. We say, if it's divided in 3, if it's divided in 4, if it's divided in 10, whatever. We would choose convenient division so that child does not get into a fraction situation, because that is not what we are testing at this time. All right. Now, the situation that we have in algebra, big is generalization. You have to see some basic thing as a model. We can see if we have the volume of a cylinder, right, with changing heights, we are going to get correspondingly changing volumes. Because the base itself would be the constant. Yes? Okay, now let us look at something that students coming from primary schools would be familiar with. Let us look at a square and give it a regular number. Hello? So give it a number of what? 2? 2? Give it a number 2. So we're going to find the area is, so if we have a square and the side length is 2, then the area is
4 units squared.
4 units squared.
Yeah.
Yeah.
Right.
Now suppose I double the, well, put the first one down first. Area of a square with side 2. What about the area of a square with side 4?
16 units
squared.
All right. What about area with side, what? 8, since I'm doubling.
64 units.
What is the pattern developing there from the first to the second to the third so far?
Multiplying the length by the width.
Yes, but I'm saying
Incorporating the formula.
where they have to know the formula, yes.
Yeah, so you incorporating it all 3 times.
All 3 things? Yes, we have to use the area in all 3. But what are you noticing?
The original area, it's multiplied by 4 times what it was for the second area, and 4 times what it was for the second area to give the third area of 64 units squared.
Yes, so you see what is happening? Can we make a little generalization there that if one does what?
Double the area. To double the length, you have to multiply the area by 4.
Okay. You are warm, but you're not sizzling. Because I think, say it in the way we did it. Say it in the way we did it.
As the length increases by 2 units for each of the squares, the areas increase by 4 times.
No, it's not increased by 2 units.
As the lengths of each square increase by 2 units, the areas of the squares increase by 4 times, the original area.
I think we were saying, don't say increase by 2 units because we doubled the size of the square. We did not just increase it by 2 units because we went to 2, then we went to 4, then we went to 8.
Well, as the squares are double, the areas are increased by 4 times the amount.
Yes, as we double the length of the side of the square, the original, the given square, the area is quadruple. Do we see that? All right, now, if you were an interested student, what would you want to investigate? Maybe since Jeffrey Ann brought up the increase the square by 2, look at what happens. That's an investigation. Do we see that? Problem solving as a close-ended answer, right? Hello? Class?
Yes, yes.
So if we are at 2 and we increase by 1, it would be, what is now the new length for the side of the square? Do we see that? Hello? Class?
Yes.
Should have 3 by 3, which is 9 units.
Right. Okay. So we go from 4 to 9 to
16.
Yes, because we're increasing by 1 according to Jeffrey. Right? Do we see that? Hello. Right? So the thing is, we have to be careful what we say. We have to be very careful because if we double side, the area is quadrupled. If we add 1 unit length to each side, then we have a different kettle of fish. Do we see that? Right? But let us investigate something else. 2 squared is 4, right? 3 squared is 9. 4 squared is 16. 5 squared is
25.
So that's one way kids can learn, the squares of numbers. Do we see that? So here we have a situation where we are going to be looking at, squares of natural numbers. Because obviously, if it's a square, it has the same length for all sides. All right? You can design your own set of number tasks, but if you're going to define them, you will have to make sure that you work through them so you know you've gone down that path already and you know how to present the situation and how to guide the conversation as it comes up. You notice, Jeffrey, and I'm not trying to put you on the spot because you're one of the ones that participate a lot more vocally, yes. But the minute you say add 1, it changed the picture. Add 1 unit to each side, it changed the picture. So we have to walk through whatever it is that we are going to be giving our students to do. So we know what the outcomes are and we can guide them to that point. The thing is that what we are trying to show them is that it's the same thing they learned. I don't know if they learned squares in primary school. but multiply a number by itself. We can call it that. They can do that, can't they? And they have to do it when they were learning their times tables, right? They have to do 2 squared because 2 times 2. They have to do 3 squared because it's 3 times 3. So we do not have to introduce indices in the primary school, but we can say multiplying a number by itself. You're planting seeds, and hopefully they will grow up into trees and bear fruit. Okay? Now, we're looking at that, and we just express some generalities. Now, at what level they start to look at functions in high school? At what grade? When they look at the parabola, with y equals x squared plus ax squared plus bx plus c. You teach a 10th grade, Jeffrey Ann?
Yes, I do.
Do they introduce variables at that point? I mean,
Yeah.
Functions.
Yes, we introduced it at that point.
Okay. At grade 10 or grade 11?
We introduced it at grade 9, in fact.
Okay.
Towards the ending of grade 9, we just do the basics with them, though.
Okay.
And then we build on it in grade 10 and grade 11.
Okay, so the thing is that we have to look at all the equation balancing and all of that, after we get to the understanding of variable and transformations and the notation and so on. So I'm doing that in 3 seconds, which is not 3 seconds, it might be our whole grade level. But we are going to move on to functions because we need to be able to solve equations, simple equations, or first degree equations. But we are going to be looking to the ascendancy of the function concept. We are looking at the function concept. We have to go into its construction. It is function and the information that goes with it and the familiarity and everything is considered a part of algebra. It's considered a part of algebra. It's a fundamental object of algebra, functions. It must be presented at some time in algebra because a function can explain a number of things. And by the time you reach function, the student should have graduated in their knowledge from just whole numbers to some other numbers, including the reals. Because whenever we are on the number line and we select the points at the end of each unit, like 1, 2, 3, 4, we're still dealing with whole numbers, yes? But the beginning, when we want to draw a line, then we start to deal with the set of
integers.
When we draw a line in the coordinate plane, we are going to be dealing with
integers,
yes, and what other numbers? If we draw a line, a continuous line, we're dealing with what set of numbers?
rational numbers,
Real numbers.
Real numbers. Because we are including all of those that you have mentioned. We have included the integers, we have included the rationals, we have included the irrationals, and all of those babies come under the real numbers. The only thing that is outside of the real numbers are the complex numbers. And so we find that we have to introduce some of those in order to get to the explanation for why we can draw a line in the coordinate plane. Language and technology has made this very easy to deal with. But alas, we might not have those devices and tools in the high school that we teach. And so therefore, we have to personally introduce and deliver on the concept without the aid of tools, the ICT part. Yes? Hello?
Yeah.
Yes.
And then we have to search for values in there after a while. But just to develop the the graph itself, we have to introduce some new vocabulary. We have to introduce, do we hear about ordered pairs in the grocery store?
No.
They only hear about it in the math classroom or maybe another science class, but ordered pairs is mainly in school they come across it.
Only in school. So let me ask you this. Let us not go to ordered pairs yet. Let us go to the coordinate plane, right? The coordinate plane, but coordinate means 2. We're not going into 3 dimensions here, okay? We are introducing the coordinate plane. How would you introduce it? Using everyday examples. What would you, is there another name that you could use for origin? Starting point.
Starting point.
Starting point. Do you think any kid on earth doesn't know what a starting point is? Any kid on earth, right here is the starting point. Do they race each other on the playground in primary school?
Yes, they do know. They do know.
Their own race, because sometimes somebody wants to show marcha there or fast there or whatever, and they set up their own races. It hasn't got to be the Olympics before they see the starting point. They make their own. I race it to that tree over there, or I race it to the wall, or something. They know a starting point and they know an ending point. When you're doing geometry, you can use that for segments, to start and end segments. Okay? Do not leave the regular atmosphere. Do not go in the stratosphere with them. You know, if they make a little race between themselves, they are traveling from point A to point B. That's the destination. Okay? So you tell me now how you would tell them to find a point in the coordinate plane after you describe and you talk about quadrants and you talk about all of this. How would you tell them using the phrase starting point? You also have to explain order, which might not be that difficult. But you need to explain it in real life. Pardon me? If there's order, then there is what? It's not any old way. It's a special way, right?
Less confusion. So
Pardon me?
if there's order, then there's less confusion. Maybe you can tell them.
Yes, you can have a talk about order. If I say line up, is that order? If I say line up, is that order?
No, if you tell them how they're supposed to line up, in what manner, then that's all.
So if I say to them, if I say to students, we're going to the auditorium or we're going to, I see some devotions where the classes line up, the girls in one line and the boys in one line. So you can say line up. If you say line up, all you do is get one behind the other. But if I say line up from least to greatest, or whatever I want to say, from east to
From shortest to the tallest.
yes. So the thing is that when you have order, you see that there is a different thing from your saying lineup. So order pairs mean that there is a specific way to express that. But I want to know if any teacher here in the sound of my voice can tell me how they would introduce this business of order and tell them how to remember which one comes first. I know some people say stuff, but I want to hear if you have something in your arsenal of tools that you could explain to the student in real life terms how you know which one comes first.
I usually tell my students X comes before Y in our alphabet. So
yes, go on.
When you're teaching them to plot points, so it's always X first and then Y. So an ordered pair is always made up of X coordinates first, then Y coordinates.
Mm-hmm. So the thing is, you give them a little mnemonic or a little thing to associate the order with, and you can say, in the alphabet, X comes, that time you have already identified the X term in very boisterous terms, so they won't forget it, right? So, how would you describe the X-axis compared to the Y-axis in real life terms?
The X-axis, it's the horizontal axis. I usually tell them, try to remember the sun rising on the horizon. That's a comparison to the X-axis.
Oh, all right. But X-axis, east, this is west, north, south, under. Okay, anybody else has any ideas? Hello? Hello there.
I'm not sure if this relates to me teaching at the primary level, but in terms of ordering, maybe I can have the students line up and illustrate this using lining up.
I wanted to give them a clue as to how to remember. Horizontal is a good word, but is there a way to tell them otherwise in something that they can remember? A little tool.
Sunrise? I don't know.
Up, down, down.
I normally use lining up. Students line up on a line. What comes first, second, line up to the left, line up to the right.
Okay. Anybody else have any input?
I'm thinking for the first part of the ordered pair, that's across, and the second part is up or down.
Okay, that's one way. But generally, I always said you always creep before you walk. Typically people creep before they walk. So they're going horizontally, they're still there. Or if you're lying down and you stand up. So you remember the first one is that you're lying down. As a baby, you didn't stand up yet. And afterward, you stand up. So when you're lying down, that is the horizontal. And when you're standing up, because children, after a while, they pull up on the side of their crib or playpen or whatever. Or if they're on the floor, they would pull up on a chair or something. So I try to remind them that, that is how we remember the x-axis when we're really young babies. And then when we become 2 years old, we can stand up. So we have the creeping before we walking. And I do not call it a rigid. Somebody told me starting point. You did, baby? What did you say starting point? Starting point is a good place. Because what happens, people do this in school, in the classroom. And you can make a big organ pair using masking tape on the floor, so they can actually walk it. So I must label my axes. Hello? Anybody who gives me anything without labeling the axes get marked down. So if I have this right here, and I deal with the first quadrant, I have to name the quadrants and everything. So I said, this is your starting point. And if you want to find, some people say 3, 2 is right here. Students don't know how they got there. Do you see what I'm saying? You have to actually crawl here. That's on your all fours, right? But I want a 3. You're all threes. And then you stand up 2 units high. So they have to know that from the starting point, it just didn't drop out of the mid-air. You have to start at the starting point that we call the origin. But little people might not even be accustomed, because you see, they don't get any reinforcers with these vocabulary items and these notational items in the wider community. They don't find it in the drugstore, they don't find it on the playground, they don't find it anywhere. They're going to find it there. So what you're doing is matching up some structures for them so that they can see it. And then you can introduce that. And then you have to go to the whole situation of explaining how you derive your ordered pairs. And I know I've seen some books that have different ways of doing it. They make tables, they give place for calculation, and they give the output. Now, what is 4 o'clock? Couple minutes to 4. Okay. So just to say that when we are talking about ordered pairs, we must have the starting point mentioned. It just didn't come up. I have to walk 3 or however many units in one direction, and then I walk in the other direction. That's how come I make that. Because when it comes to finding gradient, you call it, with slope or gradient, you're going to find that this would be very, very helpful. And you have to teach them how to get ordered pairs from the function. And function is a whole nother stuff that you have to explain to them. And then we have to look, when we come back from lunch, families of functions. Families of functions. And then we're going to move on to number sense, and you're going to have an assignment that you have to do right now. Okay, so here we go. You have a half an hour until...
Dr. Nelson,
yes.
We received the assignment too, but on the assignment sheet has using websites for part A, using websites given to determine the use. Are you going to be giving us websites?
No, one website, but I say you can do a little research on your own based on the topic so that you can have additional comments. Because you see, what I do not want in this course is that you become a reporter. When you're a reporter, you just report what your eyes see, right? In English. since we are English speaking country. But the thing is that when you become a part of it, you get in a little bit deeper and it's reflected in the writing. When you have some more, you delve deeper. Okay, so you have to find some websites on your own and put them on your reference page so that we can all go to it if we need to.
Okay, thank
you. I don't want you to be a reporter. I want you to be analytical based on the research. All right. So when we come back at 4:30, we'll be looking at functions in not so greater detail because I think it's from 9 to 11 because it's on CXC functions.
Yeah.
Okay.
In the second part.
And the nature of mathematics, functions talk a lot about stuff that we do, like radio waves and, all kind of waves, and that's calculus anyway. Pardon me?
No, so the Fourier transforms.
Yeah. Yeah. I don't think I have any lunch, but if you're going over to see if you have lunch, I don't think I have any. But anyway, we'll see. Tell them to give me my lunch. Good afternoon, everyone. Again, we're back. We're just waiting on 2 people. Okay.
I was planning on these every day.
Okay.
Okay, I think the full contingent are here -1. The full contingent is here -1. Functions are multifaceted. Okay? How many ways you can represent a function? Because we can make links between representations so people get to, you know, feel a lot more comfortable in, you know, these different representations. Just think back on your own experience. Tell me how many ways you typically represent a function.
Mapping diagrams.
Really?
How do we know what to map?
Ordered pairs.
How do we derive the ordered pairs?
From you're usually given a function and a domain to work with, and from the domain you find the codomain. That's how you find what to map onto. So you get your ordered pairs from your domain and your codomain.
The range.
Well, yeah, range.
Yeah, but what I'm saying, go back in your brain and play a tape of your experience. What is the first way you see the function represented?
A mapping diagram.
But you can't map something out of thin air. So how was it first represented?
They give you a relationship.
Which
And
is called,
say again?
Which is called the relationship, which is called what?
The relation. I don't understand.
Functional notation. Using functional notation.
I don't get that. To graph a straight line, right? To graph a straight line. How was it first presented to us?
Form of an equation.
Yes, an equation used numbers. So we said first representation is numerical, right? First representation is numerical. We get something. Your internet connection is unstable. So you get a numerical representation. So you get it in the form of an equation. Or they can tell you about it, right? How could you tell me about a function that in real life without using the word function. Suppose I have 10 chairs in a room and I have 10 people. What kind of function is that?
1-to-1.
Yes, so I can tell somebody about a function without saying the word function. That's why we can develop the ideas, right? Anybody knows musical chairs?
Yes, we do.
Yeah.
Okay. The idea of musical chairs is not 1-to-1 because somebody is going to be left out. Do you think about these things when you're talking to students, or you just go into the book and get lost there in that world?
Yes, we do think about these things. Well, I
See, the thing is that you can talk about a function and don't say function. You can plant a seed because little children know about musical chairs, right? They don't know when the music is going to stop. But whenever the music stops, we're not going to have a 1-to-1 function because somebody has to leave the game. Isn't that true? So we can have 1-to-1 and all the other stuff that we can. 1-to-1 and onto. We can have a constant function. We can have all of those things. So you can talk to somebody. So the first thing we do, you cannot jump to ordered pairs because what are you ordering according to what rule? A function is a rule that establishes a relationship between two sets, which would be the domain and the range, yes? Or the domain and the codomain. The thing is that we have a numerical representation at first. And probably we go into the algebra of it, right? We go to the algebra of it to determine the what? The ordered pairs, yes?
Correct.
Yeah? What you're saying, Jeffrey?
Saying that's correct.
Yeah. And then after we develop the ordered pairs now, we have to know how to locate the points. And the first point is on the horizontal axis. Because we have now reached a place where we can describe it as horizontal because we are finished with our creeping and walking and lying down and standing up and wearing a belt or a tie. A belt is the what axis? X-axis, and a tie would be the y-axis unless you're using the tie as a belt. Some people do. Some people use ties for belts. You ever seen that?
Yeah, I'm not people on the streets.
Yes. So you can use a tie for a belt, but if we're using it in its typical, for its intended purpose, then we have a belt would be the horizontal and a tie in its intended place would be the y-axis. And then afterwards we get the graphical because we're going to draw a picture. So we can go from numerical to algebraic to graphical. Or we could go in any direction. If we are given a graph, we could try to read the graph for its the points where it passes through the ordered pairs that we can read. Because sometimes it's in the middle somewhere of one of the spaces and we can tell exactly what it is. Function graphing technologies tell us a lot of stuff, but typically you do not use the graphing calculator in the high school. And so I would have to limit comments to programs like GeoGebra and those kinds of things in order for students to appreciate what happens as the changes occur in the representation, how the graph is represented, we should be able to talk about the changes that would take place. If you take a multiple representation approach, right, when you're teaching function, it's often pointed out that students should do tasks or teachers should provide teaching examples that you're making links across various representation of the function. So you can have the function, you can express it algebraically. Oh, when I tap this, oh, I see. I tap my book and it changes on the screen, like so. It just changed a while ago. So, sorry. So if you can, it's best if you represent this thing in multiple ways so that a child can get an example. Now, a child who sees y equals mx plus b, they should not have to graph it to see that it is a straight line. And if they see y equals ax squared plus bx plus c, they should not have to guess, because they should start out knowing that there's going to have a curve and it's going to be a parabola and it's going to open upwards. All of that has to be taught by the 11th grade. If there's a negative sign in front of the leading term, it flips over and spills whatever is in the cup. So we should know about families of functions. So right now, what I want you to do is to write y equals mx plus b on your paper. And take about 10 minutes to write up and define everything that's there. We're going to talk about the different what? How many variables do we have there? How many variables do we have there?
2.
Because the m would be the slope, and that doesn't change. And b would be the
y-intercept.
So I wanted to name everything there, and you are going to say it in the strict algebraic terms, but you're going to break it down for the student to understand. Because let me say, which 12-year-old child is interested in slope? The ordinary person on the street, where would they be interested in slope or gradient? Unless it's pointed out to them. So you need to tell me everything about the entries, all the different things in that equation, and tell me how you would try to parallel it to something that a child can understand. So I'm giving you 10 minutes to do that. And then you're going to report out. If 2 people are together can communicate, you may also do so. It doesn't have to be personal effort only. At 5 o'clock, people are going to start reporting. All right, everybody, get ready to start telling me. We have to define everything in this, in the formal terms, because I know all of you know the formal terms, but I'd like to know how you would place it in a context where the students can understand it. All right? So who wants to begin? Somebody start trying, please. Which one are we going to start with first?
We're going to start with the formal one, yes? Yeah.
Yes. Mm-hmm.
In the equation, y equals mx plus b.
Yes.
Y is the dependent variable.
All right.
X is the independent variable.
Mm-hmm.
B is the y-intercept.
What you said now? B.
B is a y-intercept.
Uh-huh.
Intercept on the y-axis.
Mm-hmm.
And m is the slope of the line.
All right. All of those are perfect names. All right. Now,
Okay.
anybody disagrees with this, with the steps that Davey has, the names that Davey has assigned to the different elements in the equation? Did you hear him?
Yes, we heard him. We agree.
We agree. All right. Now, what I wanted to get is get local, get contextual, get real life situations.
Right.
For instance, not you,
Okay.
somebody else.
All right.
Somebody else. Because you might have different ways to say this.
Can I try?
Yes, of course.
The gradient would tell how steep a line is. So, for example, to explain it to a little child, I'd probably use climbing a hill.
Yes.
The steeper the hill, then that means the steeper the hill, the greater the gradient. That means for the child, I'll tell them, if you see you have to put more effort into climbing the hill, then that means that's a really steep hill, right? But if you find it's not as you can walk up that hill and it's a breeze, then it's not as, that means it's closer to the ground then.
Okay. Anybody else has something to say? I'm waiting. You have to do this in class, so I need to hear.
I would use the same analogy with the gradient, which is the hill. Like if you tell the children that the higher the hill brings you, the steeper it is, just what you were saying. So if it's not as steep, that means it's as close to being flat as possible. And also if you are walking down a hill, that would be like a negative gradient because it's going in a different direction when you go up a hill. So therefore, you will see that the values of m can either be positive or negative. So positive would mean an upward climb, negative would be a downward. Well, it wouldn't be a climb, but going down. Yeah.
All right. Anybody else?
Okay.
Go ahead. Go ahead, Mr.
No, I was moving on to the y-intercept, but if you're still on gradient,
I still need to hear somebody else talk about this. You're talking about slope, right? Are we talking about slope?
Yes.
All right, somebody else tell me something about slope. Davey, you can talk again. You're not.
I'm not accept yet.
No, you can talk.
But what I usually, I think of it as like how change, the rate of change. Like for a bigger slope, the rate is higher, and if
but
it's
you're not using any everyday nothing here.
Come on. How fast things change. I mean, kids know how quickly things change. So if it's changing rapidly, Then you're thinking
But
about
that's not
how it changed.
that is still up there somewhere. The road is fine, the hill is fine. Yeah, but there's something else that you could use. How we define slope sometimes, the most popular way we say what? Rise over run, yes. What do we have in our lives, everyday lives, that deal with rise over run? Nobody knows?
Planes, flying.
Yeah, but my kid can't relate to that. Slides, that's a good one. Slides on a playground, right? That's kind of a slope, right? That's a slope. But stairwells, though, we go upstairs and downstairs. Isn't that slope as well? Isn't that slope as well? And don't we have the rise and the run? The space between what you step on is the rise, right? Could you use iconic representation to talk about it? What would you do if you're using a whiteboard or a chalkboard to talk about rise over run or slope? We're not talking about rise over run yet. All we're doing is getting them sensitized to by using something that they can relate to, right? So, Jeffrey, and when you say hill, first of all, I would say, if I ask you to, especially if you know the area, because in my area, there's something called Queen Hill. So if I know my students know Queen Hill, I could talk about, ask them if they think it takes the same effort to walk on the road that is in front of their house versus Queen Hill, which is very, very steep. If they don't know that, probably I could use a chalk. I could say, suppose I have to walk on this road going this way, or I have to walk on this road going up a hill like that, or if I have to walk on this road, or I have to walk on this road, I would be showing them that I have to do an X and a Y. Because if I'm in the plane, my X would be there and my Y would be there, right? So if you have to go up this hill, would it take more or less than if you have to go up to this hill, than if you have to go up to that hill? You see what I'm saying? If they have to walk up here. So I could give an iconic representation and let them reason it out. Does everyone in here know that there is a rule for making steps? It can only have a certain type of slope in order to be comfortable. Do you know that there's a rule for making a wheelchair ramp? Can you see a wheelchair ramp this height?
I know about wheelchair.
So you can't, yes, so you have to obey certain rules in order for somebody either to propel themselves up there or for somebody to push them up there. To push somebody on this, right, versus this, right? Which one is easier? Can you see the board, everybody? Can you see the board? This is A, B, C, D, E. Have a conversation with them, right? Would you prefer, which one of these would you want to push a wheelchair if you had to push the person? I'm listening, people.
B.
Anybody else? Which one is definitely excluded? A is excluded?
Okay, you don't have to push.
It's excluded.
The
E.
top one.
From
Say something again for me.
E.
E.
The top one
E
is excluded.
E is excluded altogether if you're pushing a wheelchair, right?
pushing a wheelchair.
This one is out. Probably this one will be out for me too.
That is out.
Right? But
B.
B would be the ideal. Why?
F, you don't have to take as much effort to push it because it's already flat, so you just push along. Unlike when you're going up in C, you still have to exert some more effort. And if you're going down in A, you have to be afraid of the person tripling over.
That person need a seat belt, and I need to be very strong.
Yes.
Because what is happening here?
The same effort you use pushing them up, you're going to have to use it to hold them back from the
Yes, to pull them forward on C, right? Yeah. So the same thing at work here is the same thing that is at work here, and it's called what? What?
Their weight.
Say it.
Their weight, gravity.
Gravity, yes. So gravity is pulling me faster, and if I let this person go, I can go by their casket right now. Do we see that? This person, you maybe have to buy the person who's pushing them, you might have to buy their casket. Because the gravitational pull is acting in the direction that gravity operates. And so therefore, I put this thing on here and have a conversation. I must not be too quick to get into this unless they have some understanding, because now what am I going to do? Paste on a variable on it. And that's where the shadows arise. Right? So all of these lines have slopes. All of these lines have slopes. But if the one that takes the least effort is the one that is closest to strictly horizontal. Okay? So that is what I would do. You need to have conversations. Now let us move on to independent variable. Which one is that?
X.
Curleen, I haven't heard a word from you.
X is the independent variable.
Yes. Curleen, talk to me now. How would you find a real life experience to talk about independent variable? And if you have to use any other thing to compare it with, you can go ahead. In our context here, we have four things to talk about. Curleen. She's not talking to me. I wonder if she's sleeping. How about Tasha? Are you the primary school teacher? Tasha, are you the primary school teacher? No answer. Okay, anybody want to jump in the independent variable? How can a kid be told about independence in their own sphere that they can understand?
Well, from the word independent, we could use that word, the meaning in English, meaning that you're not depending on anybody. So like, if it's a variable, they should know that variables can have a specific, can have values, sorry, not a specific value, but it can have any value. So if X is independent, that means X can get whatever value that it wants. So for example, X can be 1, X can be 2, but the value of X, it doesn't it doesn't depend on anything else. So it's based on the given range they give that you want to draw your graph, but the fact is that X is independent. So it could be 1, it could be 2, it could be 3, it could be 4, but it doesn't have to rely on anything for it to get its value.
Well, you tell me something in the child's real life that they can, what you said there is perfectly correct, and I thank you. But I want you to cross a bridge now and go over and tell the child something in their environment that is independent.
Well, you can look at their home, their parents, they make decisions. Well, it will be a comparison. I would compare it with I would take the two variables, the X and the Y together, the dependent and the independent.
Perfect.
So at their home, they have to, when they wake up in the morning, their parents have to tell them that they must go to school. So they will be that they have to depend on their parents for money, for example, for lunch, right? So that is they are dependent. So it's according to how much money their parents give them, that will be the amount of money that they have. But then, I don't know, children have this thing that their parents have an unlimited amount of money. So they would think it's as independent. Their father doesn't have to ask anybody permission for anything. But whenever they have to do something, they need to seek permission. So X would be their father, for example, saying that when their father does something, he doesn't seek permission from anyone. So, and then why? Because they are limited to what their parents can make them do.
Certainly. So that's one thing that they can understand, because most mornings their hands are stretched out. Because I don't know of many families who give them the total lunch money from Monday to Friday. Probably it would be spent. Because I have a situation, well, I don't know, because this little 9-year-old boy that I told you about, I gave him lunch money for 4 weeks to take to his teacher because I didn't get there, and he bought hamburgers, like $500 a piece, and he didn't give it in. So the thing is, when I reached there now to balance up with the teacher as to where I am on the totem pole, because I was leaving. And when I came back, she said, what are you saying to me? You haven't given me any money since you gave it to me the last time. And I said to her, what I gave, and I called the little boy's name, I gave him $2,000 to give you, and it's like 4 weeks that, like 100, because he's on par. So it's 100 a day. So it's supposed to last in 10, 1,000 is 10 days, so it's 4 weeks, really? And he said that he's tired of the lunch and he likes hamburgers, so he spent the money on hamburgers. Then, when I spoke to his mother, she said, no, because I know that he got the money to give. Because she said she pinned it in his pocket so it wouldn't, get lost, if he pushed his hand in his pocket to give to his teacher. Neither his mother I got there, and he spent it on a hamburger. But the analogy that you use, the child can understand, because most children put out their hand to receive some lunch money and bus fare from their parents. So they are dependent on their parents. But the parents are self-sufficient. I don't know, they might borrow money, but that's not the child's thing. Children don't know that. But the parent is the independent one. And that means you don't need any help from anybody else. Dependence means that you are helpless as to the amount that you get, which is the same thing as why. Because once you put this equivalence relationship in place, which it is, because y is on one side and mx plus b is on the other side. So you could use that variable. You can use that analogy for that variable. The m we can explain with graphs, we can explain with pictures, we can explain with numbers. In a firehouse, they have a vertical pole. They do not put steps on it unless it has to be spiraled. But they just slide down because they cannot make stairs on that unless it's a spiral on the slope. Now, here we're talking about B. Who else want to jump in now on B? B. B is the
y-intercept.
B is the y-intercept. How are we going to explain that?
That is where the line cuts or crosses the y-axis, and at this point x is always 0. You could tell the child that just like with climbing the hill, there's a certain point where the flat ground and the hill will meet. So at this point, the flat ground would represent a 0 at that point, and okay, I think I have it the other way.
Well, the flat ground is x, right?
Yes, it would be the x, and whatever value, just 1 second.
You can pick up there, Mr. Davey, if you want. How many slopes do we have? How many slopes do we have? How many types of slopes do we have? If we're going from upper left to lower right, what kind of slope is that?
It's a negative slope.
Downward.
Upper left to lower right. What kind of slope is that?
Downward sloping.
Okay. Upper left to lower right, negative slope. Yes? Now, so this one would be, right? Now, suppose I have lower left to upper right. Can you see this? From here to here.
Positive.
That's a positive slope. And if it's purely horizontal, the slope is?
On 0. So
it's a 0 slope. And if the line is vertical, it's
undefined.
Undefined. So all those words, we're not going to use them yet. We're going to talk about roads and hills and fathers and children and all of that. For them to begin to, so that is how you present it to them in words. Then you can make some drawings. And then afterwards. Now, we're still looking at y-intercept. Where in their lives they ever see one thing crossing the other in everyday life?
Roads, intersection of roads.
Okay. Yes, because you can have what they call, at an intersection, intersect, meet, intersection. I think they might know that by the time they get to that stage. The other thing too is that you have a situation where you can even use your body parts to show, like if you cross your arms like this, you can show them something. Or if you make a right angle, you can see where, so you have to use something that they can identify with, because what is the best thing can happen to a person when they see a numerical or algebraic representation of a function, they begin to visualize what it's all about. Yes? So y equals mx plus b tells me that I cannot see a curve. I cannot see a curve. And when you see that, you smile because you understand all that is going on with it. Now, let us look at the next thing that we're going to be looking at is another name for what I just described is algebraic expectation. You can know sometimes you have expectation because you see where you're going at the very outset. You see where you are going. And so therefore, you want the person to see the form of what is given and have an idea of the images for the function. Because you're going to teach your students that y equals mx plus b is always a straight line. You are not always sure yet where it will go. But you're going to know that the steepness will be there once you have done all the work you have to do. We have to talk. When I was learning to generate ordered pairs at first, I just wondered why is X independent? How come I have so much power to give it values? It was a kind of a blank spot for me to say, you know, everything else falls into place. How would you explain then? How would you explain then this idea of function to a child? You can use a picture if you want. You can use anything, but go ahead and tell me about the forming of ordered pairs. I know I'm going to get a straight line from this based on all that I have heard, right? Now, can you do any kind of illustration that will help a student to see why X can be anything it wants to be? Because that was a blank spot for me, a blind spot, until my teacher explained it. I had a good math teacher. His name was Mr. Morgan. He's dead now. Anybody, take a try, take a try. All right, let me see if I can lead you to think about this. Suppose I'm making paper clips, right? Suppose I'm making paper clips in a small factory. What is my input to get out paper clips?
Wire.
Wire. Steel wire.
Steel wire.
Yes. So if my factory is slated to make 7 million, right? But those things, they add up very fast. And another factory is slated to make 1 billion. What is the variable there? According to the rule. Now, I am not pretending that I know all that takes place, but I know a certain length of whatever is placed in there. Then it has to be cut, then somebody else has to fold it, and somebody else has to line it up. You know, because sometimes it doesn't come out like this, it comes out flat, although it is folded, right? So what I said, 7 million and 1 billion. What is going on here for all the things that have to take place to produce 7 million paper clips versus 1 billion?
amount of wire used.
The amount of wire you use. So that is where the independence comes in. Because Y takes what it gets. Once I put in all the functions and all the machines and all the parts that are made and assembled, right? So for a paper clip, I might feed into the machine a straight piece of wire. But there's some mechanisms in there. There's some mechanisms in the production line that will cut it to the stated, you know, you have different size paper clips. So you have some, if you set up the size machine, then it cuts it, say, 4 inches. Or it might be 2 inches for the smaller ones. Or it might be colored, like, you know, yellow or blue or red. So you have somebody to color it. So all that is the function. All that is the function. And it puts out a red paper clip that is 1/2 inch long. Or puts out a steel colored paper clip that is 1 inch long or whatever. So this function says, right, y equals mx plus b. All these can be variables. But suppose I have what the function is like a recipe, because you're going to put some inputs, you're going to assemble them in a certain way, and you're going to get out a banana bread or a banana nut bread or a banana cinnamon bread or a banana something bread. Different functions produce different things, but it depends on the input. The output depends on the input. So if I'm making paper clips, right, I feed the machine, right? I feed the machine some things, and a whole bunch of stuff is going on in here. Can you see my wonderful drawing? Can you see my wonderful drawings?
Yes, we can.
Yes, we can. I can see.
It almost looks like somebody's belly. But anyway, I feed in my thing right here, and these other functions take place. The coloring and the cutting and the coloring, I don't know what comes first, but say they color it, then they cut it, then they bend it, and what falls out of here looks like something like this. One more up. One more up. Tell me what a paper clip looks like. All right? So I put in the straight thing, and this thing falls out. So anything I put in here, right? I can do that. But if I want to make 7 million paper clips, I'm going to have to put in less than the person who's making 1 billion. So that is where the independence comes from. Do you see that? Now, let us look at this. This is I'm going to put color, cut, bend, and expel. Color, cut, bend, expel. How do you spell it? Put expel. E-E-L-L. Expel, right? So that is the function that goes on once I put in the straight shaft. Yes? Okay, now, y equals mx plus b could be y is equal to 2x plus 5. Right? So when I put in this paper clip wire, I have a machine that say color. I have a machine that say cut. I have a machine that say bend, and I have a machine that say expel. This one, I'm going to put in an X right here. And what is this machine going to do with the X?
Produce Y. It's going to say 2x.
Specifically, what is it going to do once
it's going to multiply it by 2 and add 5.
So that is the same functions that we have over here. So when my machine sees X, it's already set up to multiply by 2 and add 5 and spit out some number, right? So any number that I put in there is going to get the same treatment in here. Do we see that? So depending on what you want, if you want 4 or 5 ordered pairs, you can put in anything you want because it will be the same relationship because the same functional machines are acting upon X. Do we see that? In this case, X is a variable and Y is a variable because the values are changing. Do we see that, class? Hello?
Yes,
So you see that I can tell my kids this, and then when I go in here, this machine is made to do this. So what I do, I put in my input, anything I want to produce, I put in that input. And then I have some machines that do something to the input and drop out an output. Do we see that? So if I put in a 1, first machine is going to grab it and multiply by 2. Yes? And they're going to add 5. So the first thing they're going to spit out is a 7. But what did I put in? A 1. So that's how come I get my ordered pair. Yes? If I put in a 0, my machine can't do anything with a 0 because we know that 0 times any number is 0. So the machine will spit out a 5. That's another ordered pair. Do we see that? So I want a real life understandable concept for the student before I go to my exits. Right? Because so this could be a production function. Right? And when they grow bigger, this is how the problem. If I look at this as X and this as Y, the more I go to the right anywhere, the more that thing is increasing. Do you see that? So this would be like in higher mathematics, that would be like a what? A supply function. This is what I'm producing. More and more and more and more. But when the price is very high, probably demand is going to be low. So I'm going to have that. And they don't reach that in high school, but where they intersect.
The supply and demand.
Yes, and then it becomes
the point of equilibrium.
Equilibrium, right here. Do we see that? So do you see that we are building? That's why math is so beautiful. Because what I learned in a semi-abstract kind of a way has big applications. Do we see that? You see what I'm saying? So the thing is, when the thing is expensive, if this is cost right here of the item, when it's $500, I might get a lower demand than if that. And that is a positive slope, but a negative slope down here. But now I can put it, and then I get my intercepts in and everything. Do we see that, class? Then it goes into linear programming. Do you see that? Because maybe it's not just supply and demand. I have to look at overhead, and that will give me a different function, right? For light and all the other things that I put into the factory. So the thing is, what I learned down here is just a platform on which I can build some other stuff. Do we see that? So do you see that if you take the time to do this, right? If you take the time to explain something and put it in a context that they can understand, chances are that they will now understand because I am a dependent. So what is your new name? Your new name is Y, right? And the other one, my father is a independent. So my father's name is X. Yes, Mr. X. And you are baby Y, or your child Y, or your dependent Y. So the thing is, that is how we go about it. because one way, this is not the end all and be all, but just line up something they can understand. And as I tell you, as you go through life, as you go through your teaching life, never leave the place where they're comfortable without escorting the more abstract concepts with it, because it provides a cushion or a launching pad for them to understand what you're doing. So, to talk about smiling when you see a problem. If I see y is equal to mx plus b, I will do what? I'll smile, because I know if I make a mistake, I can catch myself. Do you see that? Because no corners, no turns. It must be a straight line ad infinitum. Then I teach about the effects of a negative sign, right? And so on. But basically, they know that the function is a machine. And this machine says twice what I put in plus 5. And every machine is not the same, because I'm not producing all this. Every factory does not produce the same thing. So you can say you're going to see many functions that are, different. And you will be able to appreciate the fact why they're different, because every person don't manufacture paper clips. Some manufacture pens, some manufacture hats, some manufacture cloth, fabric, some manufacture car parts, and all of those are functions, and you have an output. Do we see that? Okay. The highest that you go to in high school algebra is to the quadratic function, is it? Do you go to cubic functions in
No, quadratic.
Quadratic, okay. So let us live with quadratic for a minute. So my student knows that it's still a function, and the basic idea they're taking away from the straight line doesn't change. Do we see that? It's a function. But this one, you have to talk about multiplying the number by itself, but the function is still three things acting together to give me an output. So I have 3 machines, or I have 4 machines doing what I'm supposed to do. And if I explain it in that context, they will see that they have to work with the calculations. And that should not be difficult, because x is the same everywhere. One of them you'll have to square, multiply by something if a is different from 1. Do you see what I'm trying to say to you? Let them come in at a comfort zone. As I tell you, this lady, she taught history, and they change her names 3 times a year depending on what she's doing, because they become the character. So you must help your students to know, when I see a squared term, I know I must have how many turns? How many turns? When I'm graphing a quadratic function, how many turns should I have in there?
One turning point.
1 turning point, yes. 1 turning point. And you notice that the slope changes. And anytime you have a turning point, the slope changes, because this here the slope is going that way, yes, at a certain point. And its counterpart over here, the slope is going this way. So the slope changes. And that's how you know. And then when they get to higher mathematics, they will be able to appreciate why the slope changes. We won't go into that, because that is not a part of the curriculum. They are supposed to appreciate, however, that if you add something to the different sign to the standard, there are going to be some changes. There are going to be some changes, and you can go through all that. But you know what? If you get them to understand that when they see a quadratic, they smile because they know it's one term. Or if they see a linear equation, they know they must have made a wrong calculation if they see some turning or some corners coming up. That will be very, very good. So when we look at that, they can expect the solution somewhere how it looks, and they can realize that something that Jeff Ryan said earlier, that on the y-axis, x is always 0, and vice versa for y. So they should know what a family of the same function should look like. They should know standard, y equal x plus x squared plus bx plus c, and they should know if there are any minus signs or if there are any differences in what the differences would be in the equation, and what the graph would reflect based on that. Algebra is a very large content area, but the entry point is the most critical aspect of this area, because you need those concepts nailed down in order to move forward. It's far too large. You know, algebra is far too large to be covered in a year. So we have to select, and that is where the curriculum comes in. Jeff Ryan reminded us that they start the preliminaries in grade 9 and go on to grade 11 to take the high stakes exam, which is CXC. We must not lose sight, however, of the fact that algebra is a rich field with many possibilities for application and for addressing mathematical goals. We have to learn it through problem solving, or it's an aid for us in problem solving, because we know that we have many variables in life, and we want to know something about these variables in order to plan effectively, in order to plan our own lives, to plan at the community and the national level, and all that. The thing is that if we have a situation where our kids can begin to see the power of a variable, and once that variable assumes a value, how it changes the face of things, then we would be doing a fine job. We should also strive to reap the benefits of an organized approach as we introduce our youngsters to algebra. If we have an organized approach, we try to cover all the bases in terms of explaining each of the elements like we did in the equation, then we know that they begin to see forms, they begin to see structure. No exponent higher than 1, straight line. Exponent 2, 1 curve. If we are not getting a curve, we are in deep trouble. Okay? So that's what I want to say about that. The last thing I want to say is you should visit CAS on the computer. It's called Computer Algebra Systems. Computer Algebra Systems. It has a lot of potential for changing the teaching and learning of algebra and the doing of mathematics, which is our end game. The thing is that sometimes it is not used for all the reasons that we have named, because it's a technology, but it can be used independently, here we go again, or it can be used as a supplement to other technologies. So research it and see. Research it and see what you hear from it, and look at Pierce, Pierce, and Stacy, Stacey. 2001. They have done some research on it. Yes, look at that and you will. So, if you can link representation to the equation, you're way above the game. You give a little smile to yourself when you're in the exam. All right. Now we're coming to the power part for teacher. Who's the main assessor? The main assessor. Oh, I was going to go to numbers first, but let me go to, next time we'll do numbers. We'll finish up with assessment this time. Who's the main assessor for children in school? Are you the one who assesses the kids? The teacher? Yes.
The teacher.
The teacher, yes. Because this little boy that I'm telling you about, my little boy, he took the grade 4 achievement. And it has come to a consensus by all people who have input power that if you do not pass the grade 4 achievement, you're not going to take GSAT. You see what I'm saying? That's an assessment. But if we're talking about assessment, we have a lot of power. We used to have something back in the dark ages when I went to school for CXC, which they give you a screen test. A screen test is like a test to assess where you are on the totem pole in relation to the time that you have to go take the exam, right? You have to show that you are up there somewhere near the, where they put their plumb line, their expectation line, in order for you to take that subject. That's why you have to choose some subjects from grade 9. Grade 9? Is it grade 9, Jeffrey?
Yes, grade 9.
Yes. You begin to choose this subject, and now you're buckling down on them because you want to take them. All right? It is assessed that the child should be able to show proficiency in 2 main areas: numeracy and literacy. The government even say, you can't tell me you can't take it because I am going to pay for it. You don't have to pay for it. But if you want to do graphic arts and you want to do shop or you want to do this, go ahead. But as a society, we say that those are 2 major, and for a literate society, you should know some English, how to express yourself, and you should know some math in order to be an informed consumer. Okay? Now, the thing is, who is interested in assessment? Who is interested in assessment? First of all, it begins in the classroom. Who is interested? Are you interested in assessment, teachers?
The teacher to see how the students are performing.
Anybody else in the classroom is interested in assessment?
The students.
The students, yes. The students are interested in assessment.
Their performance.
Pardon me?
The students need to know how they perform.
Exactly.
They're interested.
And what is the most preferred way of expressing to somebody your assessment? What do you use to show them?
Podcast?
Pardon me?
Repeat the question.
You said the right thing. Report cards, yes. Now, suppose I give you a report card that look like one chapter in history, in the history book. Would they like that? Suppose you give all narratives in your report. Would they like that?
No, they like to see the figures as well.
All right. So you know what? They will go to narratives for things like conduct and what again? Involvement in school activities, extracurricular and all of that. But most people want to see a number. They want to see a number. And so teachers have that powerful pen. Teachers have that powerful pen. Your pen holds a lot of power. And it informs, and as it informs, it determines the reaction of the informant. See? The informed. Because what happens here is that teacher says 65. Another teacher says 85. Another teacher says 79. It's so easy to translate than to wade through a whole set of narratives where people will just be writing and writing and writing. And they might be saying a number of things. It might be a more detailed report. But who is interested? You can give that to me, I'll read it later, but I want to see the grade. So teachers have power. Teachers have power. Who else is interested in assessments?
Parents.
Parents, yes. And some children will go home and hide the report card because they know what is coming if the figures are not right. So parents are interested. So we call these people stakeholders. Who else going up beyond the parents? Who is
principals?
Principal. Because if the principal doesn't get the right marks, they are deprived of bragging rights about how they're doing. And
government.
Pardon me?
Government is also interested.
The government?
Yes.
Yes, the government is.
For them to.
Because, yes, they are also the ones who are interested. And sometimes, if they're not getting the right results from a majority of people, they begin to look into all different areas. Delivery, environment, resources, and maybe shift some things. Like in Jamaica now, I've heard some talk about a curriculum for boys. For boys, because boys are not doing as well historically as the girls do. So you find that they're now talking about writing the curriculum with boys as their focus. Because they think boys have an aptitude for things that are different from the aptitudes that girls display. So assessment is a very important tool. The high stakes exams, what people ask, how many ones did you get? Sometimes it depends on what it is that they want from you as a worker, right? they will drift. They will
Employers
drift
know.
to the persons who get high marks in areas in which they could be useful to their company. If you want to go on to higher education, your transcript is assessed. So is assessment, one assessment produces a transcript, and they're assessing the transcript to see if you are a suitable candidate to be admitted. And if you got admitted and your your performance is judged subpar once you're at the university, they have the option to ask you to leave. So all of that, assessment, everything is assessed. Everything is assessed. Everything is assessed. That's why sometimes you go into a store and you're turned off. Not enough people to help you, like in the hardware stores. Sometimes I don't know anything about what I'm doing. So to cut down on the number of things that could go wrong, I carry the old one to show that this is what I want, because I might use the wrong vocabulary, I might say something, I carry the screw, I might say it is 1.25 inches, they might say it's 1.5 inches, and I can't judge, it doesn't work, I carry the old one. So assessment is collecting and interpreting evidence of the students' learning when we are speaking specifically of the school environment. Using this evidence, we make judgments about the quality of learning and communicating these judgments to different audiences. And we have named our audience to a large degree already. Sometimes our audience, we make them our audience. Look at who is the audience for sports in athletes in Jamaica. Because of Bolt, we have the world, right? Because of Joyce, nobody heard her name. So sometimes it goes from the classroom level to the community level to the governmental level, which becomes a national audience. We have a national audience in Jamaica for our schools because everybody wants to get into the 10 traditionally high schools. And so they're traditional high schools. So we have an audience. We always have an audience when we are working with the children in school. Sometimes they call for workshops for teachers. Sometimes they call for workshops for principals with their management style or their hiring profile or whatever. But because assessment is first and foremost political. Assessment in mathematics is political. It is ideological. And it is cultural. Because the culture determines the curriculum. Yes? So everybody's interested. And if somebody hears that you are a math teacher, they're more impressed than if you say you're the textile
street teacher.
Yes. So the thing is, you gain more status because it's political, it's cultural, it's ideological. Because what is in the curriculum is what is deemed important to the whole culture, to the whole country. Now, the public school system is funded by the government, so you know why it is political. You know our Minister of Education, Mr. Honorable Ronald Thwaites. He has come in with he did come in with a lot of energy, and he tried to address places in the system where he thinks that the problem lies based on his assessment of or his interpretation of the scores that the students got in the different exams. He has tried to institute training sessions. He has talked about cooperation between schools, the ones that are doing well and those that are not doing well. He has introduced tablets in schools. He has looked at the whole spectrum of the educational system from the baby school, the basic school up to high school. He has been putting out a lot of energy. He has been using his public platform to talk about and to motivate, and he uses examples of successful schools to motivate other schools. He has done everything because it is political as well as ideological as well as cultural. Okay? So we look at issues other than the math issues because he's now looking at how boys learn. He's looking at equity issues in the schools based on the results that are recorded from the high stakes exams. All right? We look at the teacher, though, is at the very epicenter of this whole assessment thing because teachers set the expectation. Teachers make judgments, like if you don't pass the grade 4 assessment, you have one more chance, and if you don't pass it, then no GSAT for you, so you're going to go on to junior high. Teachers determine who is good at mathematics and who is not. Sometimes they, sometimes they stream kids based on ability levels. Some boast that they do not stream. So the thing is that teachers alone as a group has the power to help kids for their dreams to come true or to break the dream and make it a nightmare. That's why we're coming back now to our starting point. When you are presented with a group of students, the first place is not to lodge complaints. The first place is to observe at all the levels that you can and try to diagnose the problem, use the 5 whys and the 5 steps in intervention in order to get the student to perform at or near their potential. The thing is that anything we assign as a purpose for assessment, it is through our assessment that we communicate most clearly to students which activities and learning outcomes that we value. The assessment. So for instance, let me just give an example. Remember when we were doing the diameter problem? We divided the diameter into factors of 60 because we did not want to get into fractions. Because at this particular point, I am assessing whether the person is going to notice a pattern. Do you see the objective here? So I always say, divide it in 3, easy. Divide it in 4, easy. Divide it in 10, easy. I did not say divide it into 7s. Do we see? So what we're saying here is that through the assessment, teachers communicate most clearly to students which activities and learning outcomes we deem valuable. It is important, however, that our assessment be comprehensive and give recognition to all valued learning experience. Today we're talking about addition or we're talking about proportion, what is the assessment going to be? The formative assessment, what is going to be at the end of the lesson? It's going to be on what we have presented because we value your knowing this and it is communicating to you that I would like to see you be proficient at this particular thing. It also helps students to reflect on their work. They can see growth or lack of progress. They can see their ability to learn this subject versus this other subject. Because some students will do well at geometry and do the algebra it requires to get the answer. But the algebra problems, they do not like them. And many times I've had people say, well, I want to know if truck 1 leaves point A and truck B leaves that, when they'll meet or when they'll catch up with one another and all of that. They're not interested in trucking. So the thing is, teachers are powerful people in the classroom. Teachers give feedback and students know if they're mastering the skill that the teacher values. They want to know if they can judge from the assessment if the student needs more attention. And when we think the students need more attention, we talk about reteaching. Sometimes it's a whole class. Sometimes we talk about a one-on-one tutorial, or sometimes we talk about extra lessons. All of this is based on our assessment of the ability of the students to show proficiency in areas that are valued. Teacher can use various forms of assessment. But the quickest one sometimes is pencil and paper or informal assessment during dialogue in the classroom. It also informs the teacher of their planning. As I say, if you need to reteach or you need to use manipulatives, or you need to do that, right? So the thing is that we have assessment, and that is a big chunk because it happens all through the class, and there's a formative assessment at the end of class. Sometimes we look at, we want to look at our teaching style through the assessment, and we want to see if it provides an effective model of value performance, and if it's an effective model of educational practice. If it's effective. What I did today in class, this is my expectation, and this is what I am seeing in an objective way. Are they meeting the needs? Are they meeting the students' needs? The assessment that we use, you know them already. You know what is formative assessment and what is summative assessment. Will somebody give me a definition of formative assessment?
These are the mini quizzes and so on that are given on a regular basis after every unit or in between units and so on within the classroom. And summative is when you give one big test at the end of the term or at the end of the month. But the formative is what builds up to the summative assessment.
Okay, so anybody else want to comment?
Quite agree with Geffa.
You agree with her? What did she say?
She said that The summative is a test assessment that is given at the end of a term, right? So for example, a final project, or it can be a midterm exam. And the formative is what adds up. Okay? Basically, that's it.
Okay. Is there any place else in a child educational life that they give summative assessments?
Like at the end of the fifth form, like the CSEC exam.
That's correct. Yes. So it's not only in the schools, but it can be on a national basis. And because in the schools, we test what we teach as we go along, and we build on that and see, monitor the child's progress through the assessment. But when we give summative assessment, what is the function of, formative assessment? What is the function of the formative assessment versus the function of the summative assessment?
The formative assessment is more like monitoring the students' progress. So like at the end of every lesson, topic, we probably give them a little quiz or something.
Mm-hmm.
And the summative is like, it's like an evaluation, I would say, I don't know. Like just like to see what level the student is at the end of a certain period. So if it's like CSEC, it would be like after the 5 years.
5 years of instruction. Have I lost something? Can anybody hear me?
Yes, I can.
We can hear you. I think Anya's
It's
connection.
breaking off. I think the connection is breaking off.
Okay. So she said that the formative versus summative. Formative is at the end of maybe a lesson or a unit or something. I don't know. And the summative tend to be what?
A high-stake exam, something like a high-stake exam, for example.
Yeah, high-stakes exam are summative. But remember that there are different kinds of summative exams. In the school, if we say some school gives a monthly exam, some give 6 weeks, some monthly or bi-monthly or something. Those summative exams, you have a chance to go back and reteach. But the summative exam, like CSEC, you do not have any recourse. You see, you don't have any recourse. So generally, the formative has a wider scope. It encompasses more than the formative, because formative can be based on a lesson or so. But the summative seem to cover a wider area of instructional endeavor. But the thing is that after some summative exams, you have recourse. And with the high stakes exam, which is a summative exam, you don't have any recourse. Because once you are at the fifth form and you take the CSEC, that's it. Now, if you did not get what you call the subjects, there are people outside, independent of the school system, who will help you to get additional subjects. But that is outside of the public school sphere of offerings. Okay? So the summative assessment are generally higher stakes than the formative. Okay. Now, in summative assessments, there are benchmarks that they look for. You must pass it. Because as I say, it's bragging rights for everybody. Everybody. Bragging rights, bragging rights, bragging rights. And sometimes we brag as a nation. And There's an international exam that takes place every 4 years. The third international math and science, whatever. It's called Sims and Tims. And you have that kind of a situation where they say places like Japan and all of that do much better than some of the what we call first world countries and all of that. And it's monitored because people want to wave the flag a little bit faster when they come in at the top of the totem pole. The math and English are two things that we value, and if your child got those two, they say, you know, she got 5 ones including math, or 5 ones including math, and you know, it's bragging rights. Okay? So the National Assessment Program allows comparison across Jamaica, hence the emergence of good schools and not so good schools. And so it is a system of accountability for meeting priorities set by the government. That's what we have to deal with. That's the hierarchy of the assessment. And teachers are at the hub. So be quite aware of that. All right. So you can go to the website in your for your country, and get to the Department of Education, and you can look at what these summative assessment, the history of these things are, and what they're doing. It would be a good thing for you to do as a teacher, to see, because what they do in Jamaica, they highlight the areas of weakness for the students at the CXC level. And I'm going to tell you, it starts from decimals and fractions as some weaknesses, where some weaknesses lie. To review and reflect, and then we are going to go. Research your national results, right? Of the CXC, because that is your national test for the secondary school. And interview the mathematics coordinator, if you can, sometimes you can't, right? Curriculum coordinator and mathematics teachers. Who is providing the results of tests? And how does this happen? You can find out the path it takes. That's one question you could answer. How do the school, mathematics faculty, and teachers use these results to inform school and classroom mathematics program? That's where you're going to lay your hand, where you're going to look at where the weaknesses are in the performance, and you are going to be critically aware of that so that you can try to plug these holes, especially if you're in the 7th grade, because if you get things straight there, you're better off. We have already decided in this class that to widen the problem-solving approach in our schools, the curriculum writers have to cooperate. Because now we are into open-ended questions. No, we're into closed-ended questions based on how the curriculum is written. And remember, problem-solving and investigation are critical areas where we should have the kids to develop their skills. You can determine what changes you need to make. And if you're working under the same topic, you can make those changes, as we have tried to do. Like ask the 5 whys, use the 5 intervention options at our disposal, as we discussed in this course. And you can start in your classroom. Do what you have to do. What changes have I made? That is a question that you're going to ask yourself. What changes have I made in the teaching of mathematics to improve student performance? I suggest that you begin to look at there. What you call this thing that go up in their brain here? Executive functions. Because assessment is so important. This tells me that we have to make sure that we are covering the curriculum, but we are covering it from a slightly different perspective. Evidence-based judgments come in models. We have norm-reference tests, we have criterion reference. I don't have to tell you what those things are. Everybody knows the difference between norm-reference and criterion reference. I'm listening. I'm listening. We have lost everybody. 2 microphones are there, James and Curly and Jeffrey and Diane.
I don't know.
Do we know the difference between norm reference and criterion reference?
No, we don't.
Okay.
No, we don't.
All right. Well, you're going to know now, and you will never, ever say that again. Norm reference test compares student performance with that of other students on the same or similar task. So the GSAT is a normed reference test. Because you teach about all kind of stuff. I even learned a new name for, we used to call them, is maroons called tainos or Arabs called tainos? Arabs called tainos. I didn't know that. So the thing is, norm reference is what the expectation of the knowledge base of students at similar tasks. They should know this. All the 9-year-olds should know this. All the 10-year-olds should know this, right? Students are ranked from lowest to highest performance, and grades are then awarded based on some predetermined distribution. Sometimes it's on, you know, from this to this is an A, from that to that is a B, and so, right? So what happened, it's a means of distributing merit. So you got an A, so you belong to this place, and you got to that, and so on and so forth. So the thing is, norm-reference test is what, on a national scale, what the students should know. Did you get that? Did you get that? Yes or no?
Yes.
Yes, we
All right. Criterion referencing judges the scores of performance in relation to a set of topics. Like if you were to teach solving simple equations, you're going to test what you teach. When you test what you teach, that's a criterion test, a criterion-based test, or criterion reference test. You want to know if they can do the transposition and isolate the variable. That's criterion reference. That has nothing to do with the rest of the people, because today I taught solving equations with 1 step. Tomorrow I taught involving 2 steps. The next day with the variable on both sides of the equation. I'm testing you to see if you understand all that. That is criterion reference, right? It's predetermined criteria. If students meet the criteria for a particular grade, right, then the grade must be awarded no matter how many students have also met that criteria. So criterion reference is like your formative assessment at the end of the class or at the end of the month and so on. What did I teach? I taught A, B, and C. Can you show proficiency in those areas. That is criterion reference. But when it gets to a national scale, it becomes a normed reference. Because sometimes the questions are about the same topic you taught, but posed differently, and every child has to respond to it one way or the other. Standard reference test is also something that I don't hear mentioned, but I know the author of this person because he taught me at American University. His name is Sadkoff. And he looked at this standard reference test and developed the principle for an assessment described as standard reference, which was introduced within the secondary schools. There are 4 basic methods, but I won't go into that. All right, so we are going to be stopping here for today. I'm going to finish this assessment, do numbers, and then get back to causes and cures and review the 5 whys, and I'm going to review the 5 intervention options. Because your final assessment, you will be given a scenario, you will be given a kid. What is the basic thing we say that the person needs in mathematics? Specifically, the big non-academic thing. Something the person possesses. Starts with an M. Who remembers? And we have 3 types of them. Memory. Yes, memory. We have, so we're going to
memory and also memory.
Memory, yes. So what we are going to do, I'm going to give you a case study where you're going to look at what is presented as the child's observed behavior and reaction, right? And you are going to look into to see if there's a memory problem there, and you're going to use the 5 stages to say if it's encoding, what else? Working memory or
long-term
memory. All right, so I want to say you have a good rest of the afternoon, the evening, and I will see you on Wednesday at 2 p.m. All right, class?
Thank
Okay.
you.
Good night. Thank you.
Good night. And another thing, even before I go, reverse the good night till I say this. If you have questions to ask, it's a good time to do that next time. All right? And remember, I have not sent out the 3rd assignment yet, but it's going to be a case study, and it's going to be dealing with the memories, since that is so important in the learning of mathematics. Because the nature of mathematics is that memory is one of the most useful tools you could have. Good night. Blessings.
Thank you. Same to you. Good night.